Hi, my name is Mike Holt, and this is the second DVD of understanding grounding versus bonding as it relates to the National Electrical Code. Now, I can always reinforce this is what you have to have. Make sure you have a 2014 NEC. Make sure you have the grounding and bonding textbook. Lay it all out. If you're watching as a DVD, put it on pause whenever you want to. If it's live stream, not live streaming, but if it's going to be on the internet, you put it on pause. As we discuss things and we move things forward, be part of the process. Don't just sit there and watch this. Make sure you get yourself engaged. But before I get started, I just want to take a moment to dedicate the work that I do and the efforts that I make to God for giving me the opportunity and the skills to help others. I'm going to just quickly introduce our video team members that's helped us. And I just want to thank you guys. People that are watching this live or people watching the DVD, they have no clue how much effort all evenings after we get done, you guys are working late. And Ryan, especially, you find out all those little tiny details. And man, these guys.
I don't know whether to say thank you or not.
Yeah, that's perfect, man.
Thank you, I think.
These guys are tireless. You understand, at nighttime, we're working and we're looking at every graphic, every tech. We're testing each other at breakfast and lunchtime. We're making sure we're doing good. And so I'm just going to start on the left-hand side, and the introduction was already done in the first DVD. Mike Pilarella, Massachusetts area. Thank you so much. Eric Stromberg from New Mexico now.
New Mexico.
Okay, Ryan Jackson from Utah. Scott Harding from Washington, D.C. area, or Maryland and Virginia, somewhere in there. And then Dennis Carlton from Colorado. So, again, guys, I really, really, really appreciate what you guys are doing for us and helping the team there. All right, let's talk about the program. Again, just to review it, the scope of this program is limited to solidly grounded systems that are operating in 120, 12240, 12208, 277 480, and sometimes people get into 347 600 volts. So all our comments are focusing on that unless we talk about an ungrounded system or we get into a corner grounded system or a high resistor grounded system. We're not talking about utility distribution systems. We're not talking about static electricity. We're not talking about lightning protection, NFPA 780. We're focusing only on NFPA 70, the National Electric Code. And on the first DVD, Article 90, Section 90.1, what's the purpose? The purpose is to make sure we safeguard persons and properties by the use of electricity, and the NEC is an installation standard. So when we install the product, it must make sure that it's going to practically protect people. Nothing is perfect, but we're doing the best we possibly can. Bonding of equipment for services, 250.92. Now, for years, I struggled with this rule to learn it, and for years I struggled with how to teach it. Before we get into it, let's understand what we're talking about. We're talking about service conductors which have no overcurrent protection on them. No protection against ground fault, short circuits, or overload. Okay, there might be overload protection at the end of it, but prior to the protection device, okay, there's nothing protected against shorts and ground faults. What you never want to do is bring service conductors into a building, because if you bring them into the building and there's a ground fault, Article 100 defines what a ground fault is, phase conductor to the equipment grounding conductor. Now you will never clear that fault. You're going to have a fire because there's no overcurrent protection from the utility to protect the secondary conductors to clear a fault on the secondary conductors by using the primary protection device. So now whenever you have a secondary fault, unfused, unprotected conductors, you have a major problem. I honestly don't understand, Scott, and this is directed kind of you in the co-panel 5, I honestly don't understand why we have this special bonding requirements for service equipment and service enclosures, because no matter, maybe I guess the concept is like, well, if we bond it a little better, that maybe we can create enough fault current that maybe we can open up the primary protection device. Maybe not, but if not, hey, listen, we did the best we possibly can. So that's the danger we're talking about. So this is bonding. It's a little bit, I'll call this service bonding. All right, let's take a look at the rule here. Here's the deal. Number 1 says this: metal raceways and enclosures containing service conductors. Article 100 defines service conductors. Simple. That's conductors right here. No overcurrent protection. Wireway, no overcurrent protection. Nipple, no overcurrent protection. Meter can, no overcurrent protection. Here's our service equipment. Main means a cutoff. There is service conductors that ends there. So you can see this raceway is highlighted in yellow. It contains service conductors. Wireway contains service conductors. All this equipment contains service conductors. Conductors leaving the service disconnecting means are now called what? Feeders. So we're not applying to that. So service equipment and service raceways. Now, here's an example. Service equipment ends the main means a cutoff. This raceway is a service raceway. Here is a service enclosure. That is the end. The wireway is a feeder. Meter can, disconnects, these are all contained feeders. So metal raceways and enclosures containing feeders or branch circuit conductors are required to be bonded in accordance with 86, not 92B. But the previous slide said service raceways and enclosures must be bonded in accordance with 92B. So the first thing we have to establish, is it a service race? Is it a raceway containing service conductors? Is it an enclosure containing service conductors? Yes. Then you have to bond that in accordance with 250.92B. Now, what does 92B tell us to do? It says, well, look, if you have concentric or incentric knockouts. I don't know if the code still uses the word concentric or incentric knockouts. Now, concentric knockouts mean this, and maybe you can help me out. Some manufacturers make these knockouts out. They are on center with each other. That is going to be called concentric. Some manufacturers make knockouts that are one end is where they connect on. I think Square D maybe does the one end. So, therefore, those are incentric knockouts. The key is this.
Eccentric.
Just
eccentric.
like him.
Eccentric. Like Eric. Okay. Yeah, thank you. Like eccentric knockouts, okay? Just not quite on center. I mean, just a little bit off to the edge there. You got that? All right. So now, if you have the concentric or eccentric knockouts, all right? Now, those tabs that are holding those rings, those tabs are not going to be able to carry the fault current. So therefore, when it comes to service enclosures and service raceways, the code tells us to do this with those. If you're terminating a raceway, a metal raceway, in a concentric or eccentric knockout, you need to use a bonding bushing and a bonding jumper right here. Bonding bushing, bonding jumper, to go to the service neutral conductor. Now, I'll make statements and I'll cover later on. We only have to bond one end of this raceway. So if this raceway is going to a concentric or eccentric knockout and the other raceway is concentric or eccentric knockout, then one bonding bushing and one bonding jumper takes care of that problem. We're done. Now, standard lock nuts is what we use in the trade, and that's fine for all metal raceways and connectors and metal connectors. That's fine, but it's not fine to meet the requirements of 250.92B, the special bonding requirements. So you can't use standard lock nuts to accomplish the bonding that's required. Now, 250.92B1 tells us that the enclosures containing supply side bonding jumpers must be bonded to the service neutral conductor. Oh, sorry. Enclosures and supply side bonding jumpers must be bonded service neutral conductor. Here we go. This is on the supply side, right, of the service disconnect. So this has to be connected to the neutral. Not only that, this meter can enclosure must be bonded to the neutral, and that is going to be 250.28, the main bonding jumper. And since this is service equipment, 250.24B requires us to put the main bonding jumper there. So there are rules already telling us put this bonding jumper. My point is this. Your service disconnect is required by 250.24B, 250.28 to have a main bonding jumper. And what that does is it automatically takes care of bonding the enclosure. Let's look at the meter. The meter used for service equipment is going to have to be bonded to the neutral conductor. So this neutral is automatically bonded to this enclosure. So guess what? Meter's bonded, service disconnect is bonded. What else is metal? Oh, we got a metal nipple here, but a bonding bushing and a bonding jumper takes care of that baby. Real simple there. Now, best way to do it is to put a non-metallic nipple here. Hey, let's say a riser. Well, this weatherhead connected to the raceway, just that mechanical connection there is fine. This raceway threaded into the hub, that is fine. The hub with the 1/4-20 bolts bonds it to the meter can, that's fine. Meter can's bonded to the neutral, that's fine. Disconnect's bonded to neutral, that's fine. If there was a fault in the meter can, fault current comes in and it goes out through the service neutral going to the where? To the source. Let's go with a scenario here. If the fault is in the disconnect goes over through the main bonding jumper, gets onto the neutral conductor, and it travels back over to the utility. And the concept here is if we bond something directly to the neutral, that it provides the lowest possible impedance path to the utility to create the greatest amount of fault current to maybe clear the primary protection device. And if it doesn't clear the primary protection device, it's just going to burn to the ground, and once it clears everything, then it will stop. Now, other fittings. Eric, did you want to say something?
Well, one of the questions was, and it was from yesterday actually, is to maybe you could go over the bonding requirements for a disconnect ahead of the meter.
We'll get that when I get done with bonding.
Okay.
All right. Yeah, Scott.
If you could go back just one slide there, Mike, and you were going over it, I think, really clearly. I think it's just important to point out that there is no equipment grounding conductor between the meter can and the service disconnect means because it's not needed. Just not needed.
Right.
You're using the grounded conductor as the effective ground fault current path. And that comes up a lot. For whatever reason, people think, oh, I got to have a green wire. Well, no, just as you showed in this drawing, I have to have an equipment grounding
I will
conductor.
make sure to cover this in 352.60 because 352.60 is PVC. And what it says is that you are required to bring an equipment grounding conductor in rigid non-metallic conduit where required.
Where required, right. It's not required here.
250.142A tells us that we can bond equipment to the neutral to achieve the bonding requirements. And so since this neutral is bonded to the enclosure and the disconnect's bonded to the enclosure, if you brought an equipment grounding conductor between the meter can and the disconnect, you'd connect it to the neutral and the meter can, you connect it to the disconnect, neutral and the disconnect, now you're paralleling neutrals.
Right.
If anything, you're violating the code because 310.10H tells you that you have to size the neutral. You have parallel conductors no less than paralleling size, 3 off. They have to be the same size. And now you got, and not only that, but equipment grounding conductors were not sized, just like equipment bonding fittings were not listed for neutral currents. We're sizing equipment bonding jumpers for fault current, which is this becomes a major deal.
It's a disaster. It's kind of one of those funny things.
My
Like,
gosh.
just don't put it in. You're actually making trouble by putting it in.
There you go. If you put an equipment bonding jumper between the two of these, the most you can do. I mean, the worst thing you can do is create a code violation. I mean,
Right.
at least the best you have done is created a code violation.
Right.
In no way did you make it better. You just created now problems inside there.
It's a mess.
So that's a mess. Thank you. All right. We talked about this. When you have a hub, you thread it in there, you're good. Don't worry about it. Weatherhead, threadless fittings, you're fine. Regular fittings, nothing big deal there. We talked about only one end has to be bonded. Well, why only one end? Well, you understand something. This meter is bonded to the neutral. This disconnect's bonded to the neutral. This raceway has to be what? Bonded to the neutral. We're not trying to carry fault current between this guy here. This is just being bonding to the neutral. Here's your bonding bushing. And then, of course, you put a bonding conductor on the lug. Now here, this is the way I would go. Okay, you want to go back?
Yeah.
Go back further?
Yeah, I think the key here is that there's different options depending on where that raceway enters in regards to concentric, eccentric, tangential, or punched. If it's a concentric knockout here, we need to clarify there's options for concentric, and then there's options for not concentric.
Haven't got there yet.
Okay, I apologize.
I'm going to get there right now.
That's where you are, so.
Yeah, but it's going to be in the next one.
Okay.
And then we'll get that summary.
Got it.
It's this one right here. If we don't have concentric or incentric knockouts, now we have options.
Right.
We can't use the standard lockdown. Should put a standard lockdown on a graphic? We can't use that. That's an X. But we can use a bonding type lock nut, and we could put a bonding bushing with a bonding jumper. Yep. As a matter of fact, I should show another fitting in there. I should show a bonding wedge with a bonding wedge without a jumper. And then back over here, one of my options here would be to show a bonding wedge with a jumper. So these two graphics we need to update. So back over here, I have options. So here you go. This raceway is entering an enclosure without knockouts. You know what? Bonding lock that put a screw. When I first was a contractor and I started studying and I learned about this, I was so excited because we used a bonding bushing, and when we did it, it was this way. First of all, there's no bonding required. And then all of a sudden, inspectors started requiring bonding. And then once an inspector started requiring bonding, then we went from the metal raceway that was the service lateral. We put a 4-gauge wire solid. We went off of that. Then we went to the nipple on the meter can side. We went through the nipple bonding bushing bonding jumper. Then we ran continued that wire, non-broken, through the nipple to the other side of the nipple, around the bonding bushing on that, then over to the neutral. I mean, 4-gauge wire. Do you realize the chances of us blowing something up by running all that wire in there? But that's what was being required. And when I found out about the bonding lock nut, I'm like, hold on. If I have no concentric or concentric knockouts, I can put a bonding lock nut? And all I need is one of the two ends? Well, at that time, the meter enclosures came with knockouts. But now they come without knockouts. So what would I do? No knockouts. I just put a bonding lock nut. Done. I find out one of these two sides don't have knockouts. Whichever one it is, do what? Put a bonding lock nut. Done. Meter can's bonded to the neutral. Done. Disconnect's bonded to the neutral. Done. I'm finished. I would not want to run a wire anywhere inside that equipment. Now, this is a bonding lock nut. Let me tell you a short story about myself as an electrical contractor. When I learned about the bonding lock nut, as soon as, 4-gauge wire, I stopped that. I went ahead and I put bonding lock nuts on my equipment, and I was like ecstatic. The electric utility comes out, and they said, we're not giving you power. I said, what are you talking about? Because you got to put a 4-gauge wire, and they're trying to do this whole big configuration. I'm like, that's BS. I bought the meter. I put on the disconnect. I bought the nipples. That is not under your control. That is my equipment. I'm bonding it according to the NEC, and I'm doing it right. I'm not running a 4-gauge wire and doing all this stuff, because at that time, the bonding bushings and the bonding jumpers, if you guys know what I'm talking about, you put the wire on there, you tighten it up, and then you do what? You just adjust, and it moves. I'm like, oh, that is a piece of junk. Utility would not give me power. You get what I did? I just made it a big deal, went all the way up, and went all over the place. And guess what? They finally approved. I was the first person in my area. Somebody has to fight these people to get them to understand. I'm not going to roll over. I don't think so. So if a utility guy comes and tells me, I want you to bond both ends of the nipple, I can guarantee you that's not going to happen, because we are going to go around and we're going to fight this. Now, I got to get with a customer. I got to find the right customer with the right time, that we have enough time to play with it, because he doesn't need the power right away, and he's with me. He doesn't like people telling you what to do when they have no authority of that. So this is an NEC. The utilities have nothing to do with it, because they have no clue what they're doing when it comes to the NEC requirements and grounding and bonding, and so therefore they have nothing to do with that. So I put my bonding lock nuts, I got my finals, and guess what? Everybody started following the path afterwards. And that's okay. You need people like me to fight to make things right. This is a bonding wedge, and I learned this morning a little bit more about this. And Ryan, you checked it out, and you found, okay, as we got information from our streamers, this thing can be used around, if it's used around concentric knockouts, let me go back to some slides. If it's used here, then I have to use a bonding jumper.
Yes.
But if this is used where there's no ring knockouts, then it serves the purpose as a bonding lock nut. Oh, it serves the bonding purposes.
It meets the bonding requirements.
But watch this. If I use this, then I have to use a standard lock nut.
Yes, I would agree.
Because here's what happens. Well, when would you use a wedge? It's called a wedge. Here's what you do. You get it all done, the inspector comes out and says, you didn't bond that raceway. Like, what? You didn't, are you kidding me? My guy didn't bond the raceway? Now you got to say, power's on, or everything is a big deal. You don't want to take everything apart. Just loosen up, take the plastic bushing off, right? Loosen it up, loosen up the lock nut, get your wedge, slide the wedge inside it, drop it down, put your lock nut back on, put your bushing back on again. Come over here, take a look at the graphic, tighten up that screw. That wedges, right? This wedge to the raceway. Then you put your bonding jumper, if it needs to be a bonding jumper, if that's what the application is going to be, to take it back on. Method of bonding at service. Here's a rule. Bond one end. Here, your downpipe. You stub down and you get PVC at the end. Well, what are you going to do? Bond both ends? No. You connect the raceway and you put a bonding lock nut, you're done. A nipple. The best thing. Now, I don't like bonding bushings and bonding jumpers. I'd find one of these two sides that do not have a concentric knockout, and I'd put a bonding lock nut on there. That's what I would do. Okay, yeah, Scott, before I get off that.
Just one thing before we move off this section, and you're right, it is a section that gets a lot of confusion on. One thing to remember, you only come here if it's a service. Too many times I've seen people on the secondaries of transformers, and they're getting confused, thinking, this is just like a service, no overcurrent protection, and they're messing around with bonding bushings on secondaries of transformers, or even doing it at a remote building. You've got a remote building served by a feeder, and they're still putting out, no. Service. If there's no utility, no service, that's the only time this matters.
And we've actually talked about this in multiple times. You need to know what the service is, right, Dennis?
Right.
It comes from where? From the electric utility. There is no overcurrent protection. This is a dangerous situation. This is special bonding. This is not the secondary transformer. Secondary transformer is feeders. This is not from a generator. That's feeders. This is not a wire that goes out to remote building disconnect or the panel board. That's a feeder. This only is services. Ryan?
you know, you're right. People screw this up, and it's hard to even teach on it. But boy, you really distill it down to one thing. If you have a raceway going to a service on the supply side of the service, meter or disconnect, you have to bond it. Period. The only exception is if you're going into a threaded hub. That's it. Other than a threaded hub, you have to bond it. I don't care if you punch it, knock it out, drill it, concentric, eccentric, tangential, whatever. You have to bond it unless it goes through a threaded hub.
A standard lock nut is not sufficient.
That's right.
Brian is saying there, a Myers hub is not a threaded hub.
Yes, good point.
Oh, good point.
Good point.
250-94, intersystem bonding termination. An external accessible intersystem bonding termination must be provided at service equipment and disconnecting means for building supplied by a feeder. So here is a device, and this thing is designed to be able to take where the code requires in Chapter 8 that we bond communication systems to the electrical intersystem bonding termination. So there's a mechanical device there. The intersystem bonding termination must be accessible for connection inspection. And I don't know if we have a rule later on. It should tell us the number of termination. What's the number of termination? Isn't it 5?
3.
Is it
3?
Is there another slide?
5.
Okay. There's 3 terminations?
Yep.
Okay, so it has to be 3 terminations. You can see. And what it does is this is a mechanical device. Actually, it's a grounding and bonding listed fitting that is connected to the grounding electrode conductor in this example here.
Or to the enclosure.
Or to the enclosure.
That's pretty
Let me
common
think.
to see.
Yeah. Communication systems must be bonded. Now, there's a note here on 250.94. The communication systems must be bonded to the intersystem bonding termination in accordance with the following code requirements. These are all Chapter 8 requirements. Satellite dishes, cable TV, and telephone. So when the telephone company gets here, here's the telephone. They have an ability to go what? To intersystem bonding termination. The cable guy, he comes in here. He connects to the intersystem bonding termination. The antenna guy, he has to take the antenna itself to the intersystem bonding termination. He has to take a discharge unit for the antenna going in. That has to go to intersystem bonding termination. The satellite dish, the mast of the satellite dish, has to go to intersystem bonding termination. And then there's a discharge unit for the satellite dish. Then that has to be connected to the intersystem bonding termination. And what we're doing is we're bringing the AC power, the antenna, the cable, the telephone, the data, anything else coming into the building. We're connecting them all to the same point. And notice how many connects to the earth? One connection to the earth. Everything above ground is going to be bonded together. What is important? Your telephone, your cable, your satellite, and anything else. And anything else that's like another circuit coming in there. That's you got to realize, you got AC power coming in, telephone, satellite, cable. These are other systems that would be possibly connected to the earth somewhere else. They're going to do what? They're going to get voltage differences between the two of them. So when you come to the premises, the moment you hit the premises, you want to bond them all together to bring all those systems electrically to the same point. And then from that point on, when you go into the building. Now, if you want to really protect equipment, you put surge protection at the service. You put surge protection at the panels. You put surge protection at the equipment. You have an intersystem bonding termination. You bond everything together. You bring into your entertainment system a coaxial cable, a satellite cable. You bring the telephone. You have the high-speed, high-definition TV and all this other stuff. You plug into receptacle a relocatable power tap that has all the receptacles in there. You plug all that equipment into that same receptacle relocatable power tap. Then where it's a satellite in, satellite out, cable in, cable out, telephone in, telephone out, you're trying to, at that point of that expensive equipment, bring everything to the same potential. And maybe you won't wipe out your equipment when there's a lightning event. But that's not required by the code. The code just simply requires the intersystem bonding termination. And Chapter 8 requires us to bond all those systems to that intersystem bonding termination. Surge protection is not required for standard power systems, but I'm just giving you some information what is being achieved or what's being attempted to be achieved here. All right, let's take a look at 250.97, bonding raceways and cables for 277 and 480 volt circuits. When there's no ring knockouts and it's a 277 480 volt circuit, then standard lock nuts are okay. But this would not be permitted if this was a service raceway, regardless of the voltage. Standard lock nuts are never permitted for bonding service raceways to an enclosure, regardless of the circumstances. If it's a 277 480 volt circuit, ring knockout. So if you go through a ring knockout, then a bonding bushing with a bonding jumper would be required. Scott, do me a favor. Take a look at 250.97. Is this referring us to 250.94B2 through 4?
92B. 92B.
92B.
Right.
So really here, this would, I could probably show that one picture where you show ring knockouts, not ring knockouts. I could use a bonding wedge here with a bonding jumper, or a bonding bushing with a bonding jumper where there are concentric or concentric knockouts remaining.
What it does is it refers you to 92B except 92B1.
That's okay, that's what I'm
B1
saying.
says connect to the grounded conductor.
Exactly. That's what I thought. B2
2, 3,
to
4. Right.
Okay. Now this is something I think a lot of people that are doing 277 40-volt circuits are failing to do, and that is to put the bonding bushing and a bonding jumper when you go through concentric or concentric knockouts. All right, let's take a look. Well, why is that? Why do we have to put bonding bushings and bonding jumpers when it's a 277 480 and it's a feeder, but not if it was a 120 240 volt? Well, this is just a theoretical thing. If you have a 120 volt fault and the resistance of the fault was a 1 ohm resistor, well, then the heating of that 1 ohm resistor would be I is equal to E over R, which gives me 120 volts, 1 ohm resistor. It would be 120 amp current. And power or heat is a function of I squared R. So I is 120. We just calculate the I at 120 squared times R, which is 1 ohm. That's 1,440 watts of heat. Now, if I had a 277 volt fault, I is equal to E over R. 277 divided by 1 gives you 277 amps. Power is I squared R. Now it's 277 squared times the 1 ohm resistance is 76, basically 77,000 watts of power. So if you kind of raise the voltage a little bit more than twice, you raise the heat almost 5 times. Heat is a function of the square of the current. You double the voltage, you're not doubling the heat. It's going up 4 times because it's a square of 2. And because of that, the code does not allow you to use concentric or concentric knockouts for 277 480 volt circuits without a bonding jumper. Now, you can get enclosures that have punch-outs, not a knockout, but a punch-out. Take a look at this rule here. This is an exception. These are ring punch-outs, I think I would call these, rather than knockouts. A bonding jumper isn't required where there's no ring knockouts are encountered. We have to look at the code book, see what it says. Or where the box is listed to provide a permanent and reliable electrical bond. These boxes have punch-outs, not knockouts. And these boxes are actually marked suitable for 270/480 volt circuits without the use of a bonding bushing and a bonding jumper. These are usually 4 square boxes or 1900 boxes, and the code recognizes those are fine.
Yep.
250.98, maintaining effective ground fault current path. Expansion fittings and telescoping sections of a metal raceway must be made electrically continuous by equipment bonding jumpers or other means. So here is an expansion fitting, okay, where you have the rigid conduit. You can see where it's actually expanded and contracted right there. Well, there's no way to have an effective ground fault current path on that metal raceway if you're having this thing slide back and forth. So you have to then have a fitting that's electrically going to bond across those 2 parts. Specifically listed, identified as a grounding and bonding fitting for this application.
Yeah, you know, we talked about in 92, and this can get so confusing. I mean, I mentioned in the other DVD, I think, I get so many questions. Ryan, when do I need a bond bushing? You know, it happens all the time. 92 for services, pretty specific. Upstream of the service disconnect, you have to bond unless you go into a hub. .97 for over 250 volts, pretty specific there too. If you have a concentric knockout that's not, you know, listed, you have to bond there. Okay, well, what about everything in between? What if it's not a service and it's not 250 volts? In other words, 120, 208, 120, 240, where we live 95% of our lives. When do you have to bond there? The code doesn't tell you, and it can't tell you. Again, it goes back to you have to have an effective ground fault current path. You have to bond when you have to bond. You look at your installation, and again, you say, look, if I touched an energized wire to it, would it trip the breaker? The answer to that has to be yes, or you need to do something else.
Okay, and I'm not quite sure where to go with that because my mind is thinking, I'm running EMT, I'm going into a box.
Okay, so your knockouts are a little bit tweaked.
Oh, you're saying where it's been impaired.
Sure.
You're saying, okay, you're saying...
Or if you've got something out of the ordinary, you know? I mean, again, the code doesn't tell you exactly every single thing that you have to connect.
Okay, I know of a case where a metal raceway did not connect to the actual box because it was a theater of performing arts.
Okay.
And they did not want the electrical raceway to be connected to the electrical system because of the 60 hertz vibration of the conductors that would be transmitted to the stage. Now, whether or not that works or not, I don't know.
Right.
So what happened was the raceways were actually sleeved through the enclosure, not making contact with the enclosure. They put bonding bushings and bonding jumpers, and then they made the connection.
Exactly.
Because there was a unique set of circumstances that we needed to bond that raceway. But normally you put a raceway in a connector, or you connect it to the box, you're fine. But there could be some other condition
Right.
that maybe you're going to go around that.
Or
So just
in-
be careful what Ryan is saying. He said, look, in 99% of the times you're fine, but there could be a unique set of circumstances that we need to do this a little different than what we would normally practice do. The ring broke. You know, you knock out, concentric knockout on a 120-volt circuit, and the thing kind of broke. And you're like, oh.
It just kind of tweaked a little bit.
It broke. I mean, I remember actually seeing it, and it broke.
Well, then you use reducing
You put it in
washers.
there, and then, no, not to reduce them, just saying you had a connector in there, and then somehow it got in there, and the thing broke, and you're like, oh, man, you got the wires already pulled, and you're like, oh, I'll come back tomorrow.
Or if you've got an underground installation, go into a panel, from a main distribution panel. It's all PVC, and then it has a 90-degree rigid metal conduit elbow that goes into the bottom of the enclosure. You're going to have to bond that. If you touch it with an energized wire, it wouldn't trip.
Okay, the key is this. We need to make sure everything is metallic. It's connected to an effective ground fault current
That's
path. On the 99% of the cases, it's a simple thing. But there can be other scenarios that you're like, whoa, wait. Then you put a bonding bushing and a bonding jump. It's a rare event that you would do it other than 277, 480-volt concentric or eccentric knockouts or other than services. But there can be some scenarios, and Ryan has brought up a couple examples that we need to be aware of. We need to clear the fault. Let's move on now to 250.100, bonding in hazardous classified locations. I'm not going to get into all the details here, but when you get into Chapter 5, there are specific bonding requirements about how to bond metal raceways enclosures regardless of the voltage. So threaded entries is one way. And then you have maybe bonding lock nuts. There could be bonding jumpers. Threadless entries are also other ways. Bonding bushings and bonding jumpers might be required, but that's all contained in Chapter 5. Let's go to 250.102, bonding jumper. Okay, bonding jumper size, 250.102. This is now 250.102C1 deals with the supply side bonding jumper for a single raceway or cable. This is service conductors. This jumper right here is on the supply side of this overcurrent device. And you size the supply side bonding jumper in accordance with table 250.102C1, which is a brand new table in the 2014 code, based on the largest ungrounded conductor within that single raceway. If this is a 3/0, well, then we go to the table. You guys can look at the table on your own, and that would be a 4-gauge supply side bonding jumper. Here's what the table looks like. Now, the important thing to understand about this table is that this is how you size the bonding jumper for each raceway. You use this table when you're sizing a bonding jumper for each raceway, and you base it upon the size conductors in that raceway. Let's take a look at the next rule. 250.102C2 says, well, what about if you're paralleling multiple service raceways? Well, these are obviously on the supply side of this overcurrent protection device, and they're routed with the parallel raceways. They're based upon the largest ungrounded conductor in each raceway. All right, Scotty, you were going to make a comment about this graphic.
Yes, if you were to, instead of choosing to go from each raceway, if you combined and did one conductor that connected all 3 raceways
All right,
together.
one bonding jumper here, supply side bonding jumper, one of those, okay?
All right, the code refers you to, the last sentence says, where 2 or more raceways for a single bonding jumper, you're going to refer to C1. C1 refers you to the table. When you look at the table, then it's the equivalent size of all the conductors. I think Ryan's running a calculator here. If you add the 3 KC mills together, it's 1,800 KC mills. Have to use a 12.5% rule. Ryan, what'd you come up with from the table?
All right, hold on. Let me see if I got here. You're saying, Mike, run one bonding jumper here that 250.102C2, the last sentence says, listen, if you run a single bonding jumper from multiple raceways, then you go to 250.102C1. 250.102C1 says you go to the table. The table has a note that if you're over 1,100 kc mils, you go in a 12.5% rule. And looking back on my example, if I had a 400 amp service conductor, I'd have run 3 sets of 600 kc mils. I'm sorry. Oh, I'm sorry. We have 400. We have 400 kc mil conductors. Okay. So 400 kc mil conductors then, Ryan, would get me, what's that number?
You do the math and, 1,200,000 circular mils times 12.5%, so times 0.125. And that gives you a required kc mil of the one bonding jumper. The required kc mil is 150,000. And here's an example again of where you got to get in the back of your code book, table 8 in chapter 9. You look down and say, okay, 150,000 circular
I'm
mils.
gonna guess. 1/0?
Bigger than a 2/0, 3/0.
Oh, it's a 3/0.
Yeah,
like
2/0's
3/0?
133, and there you go. So,
All right, that's a perfect example when you have multiple raceways bonded together. Scott?
No, I was just going to say with one conductor.
With one bonding jumper, one supply side bonding jumper.
Right.
All right, let's go to 250.102D. This is now on the load side bonding jumper. So 250.102C is supply side, 250.102D is the load side. And this one says that the equipment bonding jumper on the load side of an overcurrent device must be sized in accordance with table 250.122 based on the rating of the overcurrent device. And if I have a 1200 amp device here, in this example here, then I'd have to go to table 250.122. Looking at the table, the bonding jumper for each raceway would be 3/0. It's kind of crazy. Well, we'll stop right there.
yeah.
And, here we go. Here's the example of a single bonding jumper. If you have a single bonding jumper, well, that's still based upon the rating of the overcurrent device on table 250.122. It still would be a 3/0. Well, interestingly, on the service supply-side bonding jumper, each individual raceway size would be a certain size, but when you combine them together, it then becomes larger. But on the load side, they're individual same size, or you combine them together because on the load side, you still have the same overcurrent device. Still 1,200. Okay, bonding of piping and exposed structural metal 250.104. The key here is that water piping, other piping, structural metal in a building could become energized from the electrical system. That fault current is going to go back to the source in order to clear the protected device. If we don't provide a low impedance path to the source, we're not going to be able to remove the voltage, and then obviously we have the situation we've been talking about. So let's take a look at the graphic here. If you have metal water piping, including sprinkler piping, it must be bonded to one of the following. Number 1, to the enclosure, service equipment enclosure, which is bonded to the neutral. Number 2, to the service neutral. Or number 3rd option would be to the grounding electric conductor, which is connected to the service neutral, or to any of the grounding electrodes, which is connected to the grounded service neutral conductor via the grounding electric conductor. That is how we get the fault current back to the source to clear the initial ground fault. How do you size the wire? 250.104A tells us that this metal water pipe bonding jumper is going to be sized to table 250.66. And if you go to 250.66, it's based upon the size of the service conductors. And if we had 300 kc mils, 2 sets of 300,000, 600 kc mils, looking at table 250.66, it gives us a 1/0. This is a great example showing us that the water piping system is bonded to what, guys? What is it bonded to?
Structural metal.
No,
Yes.
it's bonded to a grounding electrode.
Okay.
Because we have
Sure.
to bond the water piping to a
Right.
grounding electrode, a grounding electric conductor, the service equipment enclosure, the grounding neutral conductor, which is structural metal, but it's the grounding electrode.
Right.
Now, here's an example of non-metallic piping, in and out, cold and hot, but yet there's a small isolated section of metal piping. You do not bond this. And when this first came out, where we had metal piping systems, then we had non-metallic piping, and then you had these individual isolated sections of metal, there were inspectors at that time, and actually NFPA gave the opinion at that time that you had to go and run a bonding jumper to each of these isolated sections of metal. Let me help you understand something, why you don't want to do that. If you have non-metallic piping and you have some isolated sections of metal, then that isolated section of metal cannot be energized because it's isolated. But if you go and you take the isolated sections of metal and you run a bonding conductor and you take it back to the electrical system, if there's a failure to the electrical system, now you have energized something that was isolated. So you never, when something is isolated, you never want to make a connection to it at all, because the best you can do is make it bad. All right, let's go on to metal water piping systems in occupancies, multiple occupancy buildings, where there's separate water piping. That'd be like a strip mall where they have a water pipe coming in one unit, a water pipe another unit, a water pipe in the other unit. Well, you can't run a bonding conductor from the water piping system. Well, you can't. It's impractical to run a bonding conductor from the water piping system all the way back to the surface equipment enclosure, the surface grounded neutral conductor, the grounding electrical conductor, or one of the grounding electrodes. And so they came up with a practical rule. It says, okay, if you have isolated piping in this particular area, then you can take that water piping and bond it to the panel board equipment grounding terminal. Now the question is, well, how do you size that equipment grounding conductor or bonding conductor? Take a look at the graphic. Store 1 has a 200 amp panel, and it tells us the metal water pipe bonding is sized at table 251.22 based on the ampere rating of the occupancy feeder over current device. Clear. You have a 200 amp panel with a 200 amp protection device. We go to table 251.22 based on 200 amps. You look at the table, it tells us what? 6 gauge bonding jumper right to the equipment grounding terminal. This is actually a picture of an inspector requiring somebody to bond a water pipe, even though it's a non-metallic water pipe. Other metal piping systems such as gas or air that are likely to become energized are permitted to be bonded to the equipment grounding conductor for the circuit that's likely to energize the piping. So when it comes to gas pipe, or when it comes to air, compressed air, or anything else beside the water piping system, we're in 250.102b, then the equipment grounding conductor of the circuit that could energize that part can serve as the bonding means. So when it comes to gas pipe or air piping or any of the compressed air, there's nothing that you need to do because it's automatically taken care of. Now, there's an informational note that was added in 250.104b, note number 2. This was added back in the 1999 code that says, listen, the National Fuel Code, NFPA 54, section 7.113 contains further information about bonding gas piping. I'm not going to get into details because this is a very interesting story and would take me about 15 minutes to explain it, which we don't have the time. But the corrugated stainless steel tube industry has this gas piping system, and they've had problems where a lightning event induces so much voltage and energy, on this corrugated stainless steel tubing that when it has that discharge, particularly where it goes in the fireplaces, where it goes in through the metal sleeve inside here, it has an arcing taking place in there, and then, of course, the place catches on fire and is burned. Class action lawsuit. They try to get the code panel to require corrugated stainless steel tube to be bonded with a 6-gauge wire to go back to the surface equipment enclosure, and the code panel says, no problem, give us the information to support this. They could not support this. So therefore, the code panel did not add this. So these guys went to the National Fuel Code and added some grounding and bonding requirements to the fuel code and what it needs to be. This is not the National Electric Code. So if corrugated stainless steel tubing needs to be grounded or bonded in some way in accordance with 54, whoever is licensed, whoever is regulated by NFPA 54, whoever does the inspections of 54, whoever does the installations of 54, they have to do the bonding and grounding. This is not an electrical requirement. This is a mechanical fuel code requirement. If I was an electrical contractor, I'm not touching it, because if I make a connection between between the gas pipe and the electrical system, and there's a fire, and there's going to be a lawsuit, they're going to sue me. I'd rather say, listen, not my code, don't worry about it. But the state of Washington actually has, in their Washington administrative amendments, I think an administrative code specifically says that you are supposed to bond the corrugated stainless steel, and they give the requirements. So there are some local codes that require it. NEC does not require that at all. Okay, bonding exposed structural steel. Now this is important in 250.104c. Listen to the words here. Structural metal that forms the building frame must be bonded. So we're talking about actual structural steel that forms the frame, and if it's exposed, well, basically all steel is going to be exposed. So therefore, we have to bond that to the service equipment enclosure, to the service neutral conductor, to the grounding electrode conductor, or to any of electrodes on the grounding electrode system. The rule does not apply to metal framing members like metal framing studs or the skin of a building. I do know of a case in Florida, actually more than one case, actually a friend of mine, where he had one of his electricians, there was a problem with the drywall screw went to the phase conductor, energized some framing, but that framing was with non-metallic boxes. A guy was hooking up a dryer. He plugged in the dryer. There was a short. The short energized the framing, which energized the metal ductwork. When the guy was leaning against the dryer that was plugged into a receptacle, the dryer was connected to a equipment grounding conductor. He went to hook up this is an appliance guy, hook up the hose to the dryer. He got killed because it was a fault of the non-metallic sheet cable to the metal framing members. There was no way to clear it because it wasn't connected to equipment grounding conductor. The state of Florida has a specific requirement that all metal framing members must be connected to an equipment grounding conductor, and they give you some options how you do it. If you put a metal box on the metal framing member at one point, that's considered sufficient to take care of that. That way, if there was a fault, the fault goes to the metal box goes to the equipment grounding conductor, and maybe that would clear. We could argue that's not a good idea, the shapement of screws, we get all over the place. But that's not an NEC requirement. NEC does, it says what? Let's read it again. The structural metal frame that forms the building, the structural metal that forms the building frame must be bonded. Bonding metal water piping and separately dry systems. If you have a transformer somewhere in the building and then there's a water piping in that area where the separately dry system supplies it, then you have to bond that water piping system, that metal water piping system, to that separately dry system, because that's where the fault current is trying to get to. It's not trying to get to the source of the service, it's trying to get to the source of that derived system. And you size that bonding jumper just like you would all the others, 250.66. Now, there's an exception. And the exception says, well, listen, if you bond the water pipe to the structural steel, well, and then you have the structural steel that's being used as your grounding electrode conductor, well, then the water pipe is bonded to the structural steel, and the structural steel is connected to the separately dry system. Well, then the steel and the water piping, they're automatically bonded together, so this shouldn't be a big deal. Scott.
Just one thing there. If, let's say, you've connected the metal water piping down at your service, okay, and you've connected your structural metal down at your service. Now you're up on the 10th floor of the building. You would have to make that little jumper connection there because the connection has to be in the area served. So it wouldn't just mean your initial point at the bottom. It has to be in the area served.
Well, you know what? Let's think about practicality. If I got this metal frame of a building and I bond my neutral to the structural steel and I bond it to the water pipe, that takes care of the service. And I have my structural steel connected to an electrode, so therefore the structural steel is an electrode. And I have a transformer on the 10th floor, and I take my transformer and I ground it to an electrode, which is the structural steel. But once I go from the transformer to the structural steel, that means that the structural steel now is bonded to the derived system via the grounding electrode conductor, which now serves as the bonding conductor on 250.104D. Then, if the water pipe is in the building, it's connected to the structural steel already at some point, then the water pipe is already at the structural steel, and therefore the structural steel is connected. In other words, all I got to do is this. Take my metal water piping system, connect it to structural steel, anywhere in the building. Okay, and I got that bonded connection. Now take the structural steel and make sure it becomes a grounding electrode. I got that taken care of. When that's the electrode, you take the service and you go to the structural steel for the purposes of using that as an electrode, but it also serves for the purposes as serving as the bonding requirements back on 250.104. But we got to make sure we size them they're both sides the same rule, 250.66. Then up on the 10th floor where we have the transformer, we want to make sure we use the structural steel as our electrode because we've already established that. And the water pipe in the building in the area served is already connected to the water pipe, so therefore all I got to do is what? Bond the water pipe to the structural metal frame of the building, make sure the structural is an electrode, make sure every separately dry system connects to the structural steel,
Then you're
and
done.
it's easy. Yep.
Then you're done.
All right.